Okay, so I would like to start to thank the organizer for inviting me to present to you the Planck results. So I will give you a very general overview about the Planck results. So it will be a slightly different talk than the one you had already. I hope you won't be bored by that. But so I will start. Okay, I will start by giving you an introduction about a brief introduction about the history of the universe. So, as you know, the universe expands, and as we go back in the past, the universe was hotter and hotter. So now, here, in this diagram, we are here. We see a lot of structures around us, like galaxies, clusters of galaxies. And if we move back on the past, there is a period here which is very early universe already, where the universe, we call this period the Dark Ages, because we don't know, we know a little about this period where the first stars formed and the universe reionized. Before this period, the universe was neutral, and if we move back on the past, there is a period where it was a plasma of electrons, protons, and photons. And as the universe cools down, the energy necessary to maintain the plasma ionized was too low, and then the electrons start to combine to protons, and all the photons were free to propagate in all the directions. And that's what we observe today as the cosmic microwave background, all this background of photons which were released when the atoms or the hydrogen became neutral. If we move back on the past, you see different epochs like nucleosynthesis, baryon formation, and there is the inflation period that is necessary. So it's a period of a very rapid expansion of the universe, which is necessary to explain the structures in the universe, and also it explains the fact that we see a very uniform temperature in the sky, in the cosmic microwave background. It would be strange to have this uniform temperature without the inflation, because you will have points which wouldn't be connected causally, and then you wouldn't expect such a uniform temperature without inflation. So, about the cosmic microwave background, which is the object of studies of Planck, it was discovered by Penzias and Wilson in 1964, and it's a perfect blackbody spectrum to the limit of the instruments. Actually, we didn't detect any difference with respect to a perfect blackbody spectrum at the temperature of about less than 3 Kelvin now. This spectrum was measured by COBE, the COBE satellite, in 1992. COBE also made a full sky map of the cosmic microwave background. This is the image you see here, right? So in this image you see a very large. This is the whole sky image. You see a very large scale structure, which is a dipole actually, which is due to the fact that we move the Earth moves in the in the frame of the CMB. So you see a dipolar structure. If you remove this dipole, you see those fluctuations here in particular, which are primordial fluctuations of the cosmic microwave background, and the amplitude of those fluctuations is 100 microkelvin, very small. This emission here is the galactic emission. So since COBE, several experiments have measured the cosmic microwave backgrounds, ground experiments, balloon experiments, and there was the WMAP satellite in 2003 who made this map here, whole sky map, and you see a very nice view of the fluctuations, very small scale fluctuations. And so those fluctuations, as I said at this amplitude, are the seeds of all the structures we observe today. So what are the origin of the cosmic microwave background fluctuations? So those fluctuations are the consequence of the metric fluctuations in the primordial universe. There are two types of metric fluctuations, scalar and tensor fluctuations that are relevant. In the standard picture, those primordial fluctuations result from quantum fluctuation which are generated during inflation. So, if you consider those fluctuations in the plasma just before the cosmic microwave background emission, as the time goes by, the horizon, event horizon grows, and the fluctuation, which are very large scale at the beginning as compared to the horizon, enter in the horizon. So the smaller fluctuations here, for example, enter first in the horizon, which is represented by this line here in this diagram. So when these fluctuations enter in the horizon, it starts to fluctuate under the action of the radiation pressure. So this is the actually the baryons oscillate under the radiation pressure and under the gravity also. And you see that largest fluctuations enter later in the horizon, just before the decoupling actually, and some very large scale fluctuation never entered in the horizon before decoupling. And you see that some scales had the time to oscillate only an even number of time before decoupling. And those scales are at their maximum amplitude of fluctuation just before decoupling. And so this explains why we see some peaks in some scales which are stronger in the cosmic microwave background, is because they correspond to those scales which have a time to fluctuate an even number of time before decoupling. So I move to the CMB power spectrum. So if you consider this full sky map, what we do is a harmonic decomposition. And actually, the variance of the harmonic coefficients is the power spectrum. And that's what we want to measure. Because if the fluctuations are Gaussian, and you will see that it's the case actually to a certain limit, for Gaussian fluctuations, all the physical information is contained in the power spectrum. Okay, so if we measure the power spectrum of the CMB, we get all the relevant information for the physics, and then we can fit cosmological parameters to the spectrum. So you see a typical spectrum here, power spectrum, right? So you see the multiple here and the amplitude of the power spectrum. And you see some scales, as I was saying. There are some peaks here which correspond to the scales I was talking about in the previous slide. So this spectrum depends on cosmological parameter. This plateau here corresponds to scales which never entered in the horizon before decoupling. So now I will introduce the Planck satellite. So the goal of Planck satellite, of course, is to measure those anisotropies to a much better resolution than the BuMap. So it was launched in May 2009, and it's orbiting around the Lagrange point L2, right? So Lagrange point L2 is here. In this, you have the sun in that direction, Earth, and it's in the axis. We had 2.5 years of operation of data acquisition, and the first cosmological results were released in last March. So you see that we needed a lot of time for the analysis. It's very complicated data. I will try to tell you why rapidly. So it's a very large collaboration, about 600 scientists, 29 laboratories, and 14 countries, mainly in Europe and also USA and Canada. And the collaboration is still working hard on the data to get the polarization. So all the data we publish is only a temperature measurement. So this is a view of the satellite. So you see the mirror here. This is a 1.5 meter mirror. This allows to have a resolution of 5 arc-minutes on the sky. You see different stages, cooling stages, and you see the focal plane here, the detectors. It's quite small, like this. And so those detectors are cooled down to 100 milli-K. So it's one of the coldest points in the universe, actually, right? Because the universe is 3K. So this is 0.1 K. So this is a zoom on the detectors. So basically there are two instruments. Here I'm showing only one of those. There is a low frequency instrument, which is made of antennas, and there is the high frequency instrument, which is more sensitive, which is made of bolometers, so small crystals, which are sensitive to photons and are warmed by photons, and we measure this temperature change. And bolometers cool down to 0.1 milli-K, as I was 0.1 K, as I was saying, which observed in 6 frequency bands from 100 to 800 gigahertz. And you see a view of the different bolometers of the high frequency instrument. This is one of the bolometers, which is what we call a spider web bolometer. We want to make this kind of bolometers because we don't want to be sensitive to the cosmic rays coming. So the photons are absorbed, but not the cosmic rays, which go through the bolometers. So as I was saying, Planck is observing at the Lagrange 2 point here, and it's observing at an angle of about 90 degrees with respect to the axis of Sun, Earth, and the satellite. And so it's like this. And this observation direction that you can see here is spinning in 1 round per minute. And as the system, Earth, satellite goes around the Sun, we observe like this all the sky in 6 months. So we have 2.5 years of observation, so we observe the sky, the total sky, actually 5 times. So Planck is not doing an image, as I say. He's measuring at a given point on the sky at a given time. And so we have to reconstruct an image from combining all the data. And this is very challenging, actually, because you have a lot of artifacts in the data which are added to the time streams, if you want. You have temperature drift, you have cosmic rays. Even if you want to avoid the cosmic rays, we have a lot of cosmic rays that we need to remove, but without killing the CMB signal. So it's very complicated. So those correspond to the different observation frequencies. So in this diagram here, you see the frequency of observation, and here you see the brightness of the different components in the sky. So as I say, we observe the cosmic microwave background, but also there are a lot of spurious emissions, spurious for us, but not for astrophysicists, emission. Like we have a strong galactic emission in the galactic plane, and also above the galactic plane that is here. Very different spectrum than the CMB. And we have other emissions from the galaxy. And so you see in those bands here, it's very, we are very sensitive to the cosmic microwave background, but we need all those measurements to be able to remove the different components. This is shown in this image after reconstruction. This is a very high frequency, 800 gigahertz image measured by Planck. At this frequency, it's here, you see only dust emission. You don't see the cosmic microwave background, so you see an image of the full galaxy. This is the dust emission. If you go down in frequency, you see the evolution, and 217, you start to see the cosmic microwave background at high galactic latitude. 143, which is the most sensitive channel, 100 gigahertz. I don't show all the channels, right? So you see, I think you can understand how we can remove the different components is by combining all those channels. Since the components have different spectra, we can do some actually linear combinations of channels to remove the components. There is no absorption from the galaxy. The CMB photons go through the galaxy without any absorption. So it's really a sum of different components. And that's what we get after removing the components. This is quite amazing because here in the galactic plane, the galactic dust, even in the highest frequency channels, is much, much stronger than the CMB. So the component separation is working extremely well, actually. This is a nice view. This is a nice proof because if it's working well in this region, we know that here it's less problematic. So this is the cosmic microwave background map measured by Planck. You see all the structures, very small scales as compared to the blue map. I can illustrate that in the next slide. And you see also very nice structures at very large scale. We see that this is quite a little bit problematic. I will show you why. It's a huge image, so it takes some time to... Okay. This is a small map somewhere in the Planck map. And you see the structures here, the CMB structures, and you as compared to the WMAP. So you see the gain here. In particular, if you compare this to the poor spectrum that we want to measure, does this peak here correspond to structures at 1 degree? Typically those ones. They are well measured by WMAP also, so WMAP is very sensitive to this acoustic peak here. But if you see those small structures here, which are very, very well measured by Planck, you don't see much of those in the WMAP maps. They correspond to the other peaks here. And so Planck is really sensitive to those peaks as compared to WMAP. And it's very good for cosmological parameters because cosmological parameters impact, for example, the relative amplitude of those peaks. So this is the angular power spectrum measured by Planck. Very tiny error bars, and we go very far. If we count the peaks, we go to 8 peaks, actually. And this is a comparison to to previous measurements and actual measurements. So the Planck points are the red one here. So we go up to here, and then the error bars start to be big. So this is a very large L, so it means very small angular scale. So we start to hit the resolution of Planck. And you see a lot of experiments. They are ground-based experiments which measure very well, actually, the very small scales. And it's very useful. It's very useful to get the NS parameter. I will show you why. So the ground-based measurements have very large mirrors, so they have a better resolution of the sky, but they are limited because the photons have to go through the atmosphere, so those experiments have to focus on the very small region on the sky. That's why they measure only, actually, the very high multiple, only the small scales. And you see WMAP points here in red start to increase basically here. So something which is very amazing about the results from Planck is that if we fit the Lambda-CDM, so the cold dark matter model with a cosmological constant, with only 6 parameters, we get a very, very good fit of the data. Right? So this is the line in this graph here compared to the Planck measurement. We get a very, very good fit with only 6 parameters, 6 cosmological parameters. So I can comment here about the fact that the error bars are large here for large angular scales. This is what we call the cosmic variance, right? It's because we only have a limited number on the sky of large angular scales, so we have very large error bars, and we'll never be able to get lower error bars with any measurements, like, except if we wait like a billion years or something like that to get a different CMB. But we'll never be able to reduce those error bars. And actually, the spectrum is limited by cosmic variance down to about here. And then we start to be limited by noise. So this is the same spectrum than before. And this is just to show you the difference between the measured CMB spectrum and the model, the Lambda-CDM model. So this is here. If you compute the significance of this, I mean, if the spectrum is compatible with 0, the residual is compatible with 0, we get a very, very good fit. Actually, except about here. I will talk to you about that in next slides. But this is showing a very good agreement between the Lambda-CDM model and the Planck measurements. So those are the 6 parameters that we fit. This one, for example, is the baryon density in the universe as compared to the critical density. We fit also the dark matter density. We fit the parameters which correspond to the horizon scale at the decoupling, so acoustic horizon size at the decoupling. We fit tau, the reionization optical death, so after the the emission of cosmic microwave background, the universe starts to reionize under the light from the first stars which are formed. And so this affects a little bit the spectrum, and we need to fit also this parameter. We fit also those two parameters, which are fundamental parameters, which correspond to the Power spectrum, the primordial scalar Power spectrum. So this is the index, and this is the amplitude. So we assume only a single Power law spectrum for the initial perturbation. And then the other parameters are derived, like the dark energy density. So this is assuming that the universe is flat. That's why we can derive the dark energy density. Hubble constant, the age of the universe, and we can imagine a lot of parameters, but those are the main ones. So about the energy content, I gave you the values before, but then you can see in this diagram the proportion of different quantities in the universe. So this is before Planck, like measured by WMAP and other experiments, and this is after Planck. You don't see much change, except that there is a little bit less dark energy, but still very dominant, right? You see the dark matter here, which corresponds to 27%. And ordinary matter, baryonic matter, which correspond to about 5%. So about the primordial spectrum, as I say, we assume that the spectrum is a Power law. So this is the parameterization, amplitude and index, -1. So for what we see is that this index is not compatible with 1, so we have a deviation from the scale invariant spectrum. Very significant deviation. So we expect a deviation with the inflation, but we observe that at 7 sigma. So it's very, very significant. You can see here what will be the spectrum. So this is not the spectrum as I was showing before, but this is spectrum times L square, just to show more the smaller scales. And you see two different fits, one with an S equal 1 in blue, and the other with an S which is measured by Planck. And you see that this, the blue curve here, and that's after fitting all the other parameters, is not compatible at all with the Planck data. So really, the spectrum, we measure the spectrum is not scale invariant. So this is the Hubble constant. This is interesting because we get a measurement of the Hubble constant here, which is different than the local measurements by looking the local objects. This is not compatible. This is not extremely significant because this is only a 2.5 sigma effect, but we see some deviation. So for Planck, what we measure is the cosmic microwave background. So this is very far in time as compared to now, and the Hubble constant is this is H0 is the Hubble constant now, right? So we need to do some extrapolation with the model to be able to predict this value. So there is some extrapolation as opposed to those measurements which are local, but those measurements have a more systematic bias, like astrophysical bias. So we try to go beyond the 6 parameters model and try to constrain some fundamental quantities like the neutrinos, for example. The CMB, cosmic microwave background, is sensitive. The shape of the spectrum is sensitive to the mass of neutrinos, actually, and to the number of species. And when we try to estimate these parameters, adding extra parameters in the fit, we see that the effective number of neutrinos is compatible with 3, which is a different result than what got WMAP. And then the sum of the masses of neutrinos is smaller than 0.2 EV, 95% limit. So it's a very, very good constraint, and actually this is the best constraint on the mass of neutrino we have. We try to look some deviation from lambda, actually some variation of some dark energy dynamics, and this is, you see that W, so a pure cosmological constant will be -1, and we see something compatible with -1, pure cosmological constant. We put a limit on the tensor modes, which is this. with the polarization, we'll get a better limit. And we try to measure the running of the spectral index, so try to see some deviation from a pure power law of the primordial fluctuations, and we didn't see any, actually. You see it's compatible, or it's at the limit, but still compatible. We have no detection of isocoverture modes, cosmic strings, no variation of fine structure constant, so everything compatible with the 6 parameters. So about the inflation, those are the constraints we get on the inflation. So this is those contours correspond to the in the x-axis here. You have the NS spectral index and the tensor to scalar ratio here, and you see that Planck is compatible with the with the simplest inflation models. So the simplest inflation models fit very well the Planck data. What's very interesting here is that given the value of NS, which is here, you see that this model here, which corresponds to a potential which is on phi square, we are just at the limit, right, of Planck. With the polarization, we'll be able, with the measurements of the tensor modes in the polarization, we'll be able to reduce those error bars by a factor of something like 3. So a detection, actually, of B modes is really possible with Planck. I go very fast on this. We measure the non-Gaussianity, so we do it by measuring the 3-point function on the CMB, and we didn't detect any non-Gaussianity in Planck. No non-Gaussian. So it's purely Gaussian, and those are the limits of FNL, which is a parameter which characterizes the non-Gaussianity. And you see those limits here, which are compatible with 0. I have to skip that, but what I wanted to say is that you have just 20 seconds. We see a small problem, actually. I was saying that the fit of the Lambda-CDM model was very good, but we see some deviation, actually, at very large scale. You see the data points, you see the model. If we vary the parameters, NS in particular, you see that it doesn't fit very well the data at very large scale. This is only a 2.5 sigma effect. It's not very significant. We won't be able to improve that because this is cosmic variance limited. But maybe with the polarization, we'll see some effects. What's very interesting is that this deviation happens exactly between scales which are outside the horizon and scale inside the horizon at the decoupling of the CMB. So there might be something here at very large scale. So I need to skip that. There are other anomalies at a very large scale, like difference in ecliptic pulse of power. You see it's quite significant, still 2.5 sigma effect. And I skip that. I'll let you read the conclusion because I think I need to finish.
Thank you. Any questions? Yes.
So I guess I have a couple of questions. So you didn't mention the overall power difference between WMAP and Planck.
Yes.
Is there any news on the interpretation of that?
So that's true. I didn't mention that, but there is a difference. Actually, Planck and WMAP data are not compatible in amplitude, even if the cosmological parameters are compatible, right? So this is maybe it goes in some directions which is not fitted by the parameters. We don't know exactly. We try to compare. We discuss with WMAP team. We don't know where the problem comes from. It could be a systematic effect. It could be a calibration. Calibration is very hard. We do that on the dipole because we are able to compute the amplitude of the dipole with the solar modulation. We think that it could come from the dipole, but we don't know yet.
But you think it's L independent?
Yeah, it's there is some, not completely, but almost. There is some difference at a large scale, I think, a small scale, sorry, but it's mainly L independent. Yeah.
So also just very quickly, I mean, you're bound on R's, of course, indirect, as you said.
Repeat that, sorry.
Your bound on the tensors is, of course, indirect, as you
Yes.
said. And one thing about it is it's partly driven by the low L anomaly.
Yes.
It's trying to cancel that.
The tensor.
The bound on R. So
Yeah.
if that's a fluctuation, then in fact the bound is weaker. But anyway, as you say, you'll go through that window with direct
That's right.
measurements,
That's
which
right.
is very exciting.
Any other last question? Okay, let's thank the speaker again.